let's use our theorem from the previous video, do some examples with it. It gives us calculations of area from polar coordinates. Let's do a really simple example here. Compute the area of a circle centered at the origin of radius r. So this is more of a sanity check just to make sure that everything is on the up and up. What do I mean by that? So of course we know area of a circle, this is going to be pi times r squared. So we're going to use our fancy formula from this slide in order and make sure we get the same answer. Otherwise something's troubling here. So an equation for the circle of centered at the origin of radius r is just little r is equal to big R here. And so that's just going to be 1/2 times, the calculation is going to be 1/2 times the integral. 0 to 2 pi is going to be 1 complete trip around the circle. Maybe I should draw a picture of that. So this is what we're doing here. 0 to 2 pi of r squared, well, that's just a constant, d theta. So when we are integrating with respect to theta, this r squared is a constant, and so our integral just ends up as 1/2 times r squared times theta, plug in 0 and 2 pi, and this just is 1/2 times r squared times 2 pi, cancel. Sure enough, we get pi r squared. So that's all on the up and up. So we should be reassured that our formula from in this theorem from the previous video is true. Okay, let's do a slightly more involved calculation here. Let's use our previous theorem to compute the area of the right semicircle with equation r is 4 sine theta. So if I draw the picture here, so this is going to be a circle of radius 2, and it's centered at the point 2, 0. It's going to be up above the x-axis. So when I said the right semicircle, this is what I'm talking about here. Okay, so let's use this. We know from here it's going to be 1/2 the integral from something to something of f of theta squared d theta. So let me write that down. 1/2 the integral of f of theta is 4 sine theta squared d theta. What are the bounds here? So we want to think about when do we stop and start and stop, I should say, picking up area. So as soon as we get theta is anything a little bit bigger than 0, we are picking up part of the circle. So theta is going to start at 0, and it's going to stop up here. It's going to stop when we hit theta is 2 pi. So this gives us our bounds and our integral. Theta is running from, sorry, I just said 2 pi. This is, of course, theta is pi over 2. So the integral from 0 to 2, pi over 2. 4 sine of theta, all that squared, divide by 2. This is going to be 1/2 times 4 squared is 8. Integral from 0 to pi over 2 of sine squared of theta d theta. Throw back to the first half of class or so. How do we integrate this? We're going to replace sine squared theta with 1 minus cosine of 2 theta. All of that divided by 2. Oh, I dropped that pi over 2 there. And so when we integrate this, we get 8 times integral of 1/2 is theta over 2. And then we end up with a minus sine, minus sine of 2 theta divided by 4. Plug in 0 and pi over 2. And we are left with 8 times pi over 2 divided by 2 is pi over 4 minus sine of 2 times pi over 2 is sine of pi divided by 4. And then when we plug in 0 here into both of those, we get 0. And this simplifies down to 2 pi. And so we should point out that this answer also checks out because this circle overall has radius 2. So the overall area of the entire circle inside of it is pi times 2 squared is 4 pi. Half of that is 2 pi. So that's reassuring. Okay, so to end this video, here is a pre-class problem. So please find the area of the region bounded by r is equal to sine of 2 theta, where theta is running from 0 to pi over 4.